Trigonometric substitution. The goal is to evaluate integrals where integrand involves the square root of x squared plus a squared, the square root of a squared minus x squared, the square root of x squared minus a squared. Consider the right triangle whose sides are a and x. The hypotenuse is the square root of x squared plus a squared. Tangent of theta is x over a, so x is a times tangent of theta. X squared plus a squared is therefore a tangent theta squared plus a squared, and this can be simplified to a squared times the quantity tangent squared theta plus 1, but tangent squared theta plus 1 is secant squared theta. So the square root of x squared plus a squared is a times the absolute value of secant of theta. We see that if x is a tangent of theta, then the square root of x squared plus a squared can be substituted with a, the absolute value of secant theta. Consider another right triangle whose size is x and the hypotenuse is a. The missing side is the square root of a squared minus x squared. Sine of theta is x over a, and so x is a times sine theta. The square root of a squared minus x squared is now the square root of a squared minus a sine theta squared. And this can be simplified to a times the absolute value of cosine of theta. Consider another right triangle whose hypotenuse is x. One side is a, so the missing side is the square root of x squared minus a squared. Secant of theta is x over a in this case, so x is a times secant theta. The square root of x squared minus a squared is the square root of a secant theta squared minus a squared, which can be simplified to a times the absolute value of tangent of theta. And so with x equals a tangent of theta, the square root of x squared plus a squared is a times the absolute value of secant of theta. With x equals a sine theta, the square root of a squared minus x squared can be substituted with a times the absolute value of cosine of theta. And with x equals a secant theta, the square root of x squared minus a squared is a times the absolute value of tangent of theta. These are called the trigonometric substitutions. For example, evaluate the integral of the square root of 1 minus x squared dx. First, we draw a right triangle whose one of the sides is the square root of 1 minus x squared. So the hypotenuse is 1 and the side is x. Sine theta is x over 1, so x is sine theta. X squared is sine squared theta, and therefore 1 minus x squared is 1 minus sine squared theta, or cosine squared theta. The square root of 1 minus x squared is now the absolute value of cosine of theta. As long as we restrict the domain from negative pi over 2 to pi over 2, then the square root of 1 minus x squared is positive cosine of theta. The integral of the square root of 1 minus x squared dx is now the integral of cosine of theta dx. But if x is sine theta, then dx is cosine theta d theta. And so the square root of 1 minus x squared dx is now cosine theta times cosine theta d theta. Simplifying this to obtain cosine squared theta and use the double angle formula to rewrite it. The antiderivative is 1/2 times the quantity theta plus 1/2 sine of 2 theta plus c. We then distribute 1/2 to obtain 1/2 theta plus 1/4 sine of 2 theta plus c, or 1/2 theta plus 1/4 sine of 2 theta is 2 sine theta cosine theta plus c. 1/2 theta plus 1/2 sine theta cosine theta plus c. This is not the final answer because the variable in the original integral is x. This expression is in terms of theta. We need to rewrite these expressions in terms of x. Since x is sine theta, theta is sine inverse of x. Using the right triangle, sine of theta is x over 1, and cosine of theta is the square root of 1 minus x squared over 1. Make sure the final answer to this integral is in terms of x. Simplifying it to obtain 1/2 sine inverse of x plus 1 over 2 x times the square root of 1 minus x squared plus c. Another example. Now the goal is to rewrite the integrand using trigonometric substitutions. We observe that there is an expression that involves the binomial x squared minus a squared, so we start with the right triangle. Since the expression is x squared minus 9, the hypotenuse must be x and one of the sides is 3. The missing side is therefore the square root of x squared minus 3 squared. Using the right triangle, we obtain cosine of theta equal 3 over x, and so x is 3 secant theta. We're going to rewrite each expression in the integrand in terms of theta, with x be 3 secant theta. And so x squared is 9 secant squared theta. Thus we're going to replace x squared with 9 secant squared theta. The expression x squared minus 9 is therefore x squared is 9 secant squared theta, and we simplify it to 9 times the quantity secant squared theta minus 1, but secant squared theta minus 1 is tangent squared theta. With the proper restriction on the domain of theta, the square root of x squared minus 9 is the square root of 9 tangent squared theta, or 3 tangent theta. We have a substitution for x squared, which is 9 secant squared theta. We have the substitution for the square root of x squared minus 9, which is 3 tangent theta. We still need dx. But x is 3 secant theta, then dx d theta is 3. The derivative of secant theta is secant theta tangent theta. The differential dx is 3 secant theta tangent theta d theta. We now have trigonometric expression for all of the factors in the integrand. The integral 1 over x squared, the square root of x squared minus 9 dx is now the integral of 1 over x squared is 9 secant squared theta. The square root of x squared minus 9 is 3 tangent theta, and dx is 3 secant theta tangent theta d theta. Cancel out secant theta and tangent theta. To simplify this, we have 1 over 9, the integral of 1 over secant theta d theta. But 1 over secant is cosine, and so we have the integral of 1 over 9 cosine theta, which is 1 over 9 sine theta plus c. Again, this is not the final answer. We still have to rewrite this expression in terms of x, but using the right triangle, sine of theta is opposites over hypotenuse, and so the answer is 1 over 9, the square root of x squared minus 9 over x plus c.